Center of mass. Now we're going to look at a solid object. So those of you that are taking a calculus-based physics class should be paying attention here. We're going to do one-dimensional objects because no point in confusing things. So this is basically a thin rod. And let's take a look at the equation we would use for center of mass for point objects. We add up, right? It's a summation, and we multiply each mass by its position, and we add them all up, and we divide that by the total mass, right? We sum up every point mass. So how would we do that with a solid object? Well, the first thing we do when we have solid objects is we pick a little location here, and we say that there's a little tiny infinitesimal chunk of mass there at the middle of this object or some point in this object, and we call that dm, some little infinitesimal piece. And what we're going to do is we're going to add up all the little infinitesimal pieces multiplied by their position. So the center of mass position then is going to be a summation, but when we have a continuous object, how do we sum it? It becomes an integral, right? It's a summation of each little piece multiplied by its position. And we're going to divide that by a summation of each little chunk. So those summations that we had for point objects turn into integrals, and we have this little infinitesimal piece dm that we're dealing with. Now, of course, we're integrating over all the little tiny chunks dm and adding them up. So what do you think the integral of dm is going to be? It's going to be the total mass of the object. So how do we deal with this dm? Well, the analogy I like to use, because we can all figure this out. Let's say I handed you a long rope, and I asked you, how much does a ½ meter section in the middle weigh? How are you going to figure that one out? Well, you're going to take the whole rope and weigh it, and then you're going to measure the length of the whole rope, and you're going to come up with a density. Usually we use lambda for density, and so if it's uniform, you're going to have the total weight over the total length. This is if it's uniform, right? By uniform density, I mean if you cut a 1 meter section out of the beginning, or a 1 meter section out of the middle, or a 1 meter section out of the end of the rope, they would all weigh the same. That's what I mean by uniform density. So for our rope, if we're trying to figure out how much a ½ meter in the center weighs, then we take the density and we multiply by the length. So we take our density and we multiply it by ½ meter, and we end up with the weight in the center. So normally we don't use weight in physics, we usually use mass. So we have mass density, and it's important that you pay attention here, because next quarter you're going to be doing charge density. You're going to be doing these exact same integrals, only instead of a dm that you're integrating over for mass, it's going to be a dq. It's a charge density you're integrating over. So make sure you get down center of mass and can do these integrals. Okay, so let's go back to mass, and first of all, let's talk about what we see when we have different dimensions. So if our object is one-dimensional, like a line. Then the density, and again this is if it's uniform density. If uniform, the density will be the total mass over the total length. And I'll just use capital M for total mass and capital L for total length. And our dm is going to be the density. We want to know how much mass is in some little tiny section in the middle somewhere. So how do we do that? We multiply our density times some little tiny section of length, and just like we did with the rope. And what's do we use for length? Usually in physics we call that ds, some little tiny length element, and it depends on what your coordinate system is. ds might be just dx if your object lies along the x-axis. It could be dy if it lies along the y-axis. It could be dr if it's a radial direction. So I'll just put ds, a one-dimensional tiny bit of length. Let's look at a two-dimensional object. So something that has area. Then our density is going to be the total mass. This is mass density, right? Over the total area. And what's dm? dm is going to be the density multiplied by some area element, dA. And that depends on your coordinate system. If you're just in a rectangular coordinate system, dA would be dx dy. If you're in polar coordinates, you'd have a different dA there. And if it's a three-dimensional object, our density is the total mass over the total volume, and dm would be the density times some volume element, dV. Now, it's pretty typical in physics to use this symbol rho for density, but some physics books use different symbols depending on whether it's one-dimensional, two-dimensional, or three-dimensional. So I'm just going to use rho. We used a physics book not too long ago that used lambda for a one-dimensional density, sigma for a two-dimensional, and rho for the three-dimensional density. But I'm just going to use rho for density, keep it a little simpler. So now we want to go back and actually do our problem. We've got a one-dimensional object, a rod, very thin rod, uniform. We'll come back and do one that's not uniform in a minute. Let's make it uniform. And total length L. And we talked earlier at the other video with point masses that the center of mass should be independent of the coordinate system we choose. So I'm going to choose my coordinate system to be right here. I'll put my y-axis here. And if the rod starts at x equals 0, then the end of the rod over here is going to be x equals L because it's total length L. And where do we expect the center of mass to be? This is a uniform rod, so the center of mass should be right smack in the center. Well, we'll see if our integral gives us the right answer then. Okay, there's some small element dm in the center here, and so our x center of mass is going to be equal to the integral of x dm over the integral of dm, and dm is equal to the density times some small length element. And what is the density? In this case, it's a uniform rod. So it's the total mass over the total length. That's the density. If it's not uniform, then the density would have to be given, and we would just plug it in. But it's uniform, so we know it's total mass over total length. And our small element of length is dx, right? We're along the x-axis here. So dm is equal to dx multiplied by m over L. So I'm going to go ahead and plug these in. So I've got an integral of x dm, which is m over L dx, and that's x is going from 0 to L. And I'm not going to just plug in capital M here. I'm going to show you that we get the mass for the integral of dm. I'm going to do it for you. The integral from 0 to L of m over L dx should give us the mass. Okay, so let's go ahead and do these. The top is going to give us an m over L. That comes out of the integral, that's constant. And the integral of x dx is x squared over 2. And we have to evaluate that from 0 to L. And the m over L comes out. And we have the, we have the integral of the integral of dx is just x. And we're evaluating that from 0 to L. And so I have m over L times L squared over 2 minus 0. And I have m over L times L minus 0. And so I have m L over 2 over m. And the m's cancel. And I get L over 2. So that's what we expected. If you come back up here, at x equals L over 2, which is about here, we have our center of mass.